And okay, let us start. Thank you to organizer for having such a nice opportunity to have a talk today. And this is a joint work with Professor Kinakov. I would present our last results. And as you can see, the title of my talk is written here. It's not. It's slightly different from the main direction of the conference, but don't be confused, because actually we will be focused on the parametrics method, very useful tool also for some statistical problems, for example. And let us start. Sorry for mistyping brackets. And let us have two ET diffusion processes. First one and second one. As you can mention, in the second part, we have not just the only one process, but the series of processes enumerated by n. And the question is how close the processes are if their coefficients are close enough. Actually, this is a natural question because when you are dealing with the ET diffusion processes, sometimes you have to perturbate your coefficients, maybe for smoothness aims or for something else. And in the end, you will be interested in how close your final process is to your previous process. So we are going to find an answer on this question, and the natural example of the simplest maybe case for this is the case if you have two Gaussian densities with different means and different correlation matrices. What will be done in this case? Of course, you should expand it into Taylor series and estimate it according to the properties of the Gaussian densities. And the key point is that this simple example is the most important thing for proving the general result. And let us be in the d-dimensional case and also non-homogeneous case. So we have vectors b, bn, and matrices sigma and sigma n as the coefficient of the processes. And let us denote matrices sigma, sigma transpose as matrices a, I, j. What about assumptions? So I should say in what sense we will estimate the difference between processes. We will do it in the sense of the difference between transition densities. So we want transition densities to exist. For this purpose, we assume the bounded and continuous assumptions for the coefficients of the first process. And also, as I've said, we want coefficients to be close enough. So we assume such condition for the coefficient b, and also hold the condition for it in the condition on its closeness. And a little bit stronger condition on the coefficients a, I, j. It's a little bit stronger than ordinary Hölder condition. It could be seen in the book written by Krylov. We need function a, I, j to be from the Banach space of such kind of function that are finite with respect to such written norm, parabolic norm. And if, in addition, we assume that also coefficients I, Ag and A, N, Ig is close enough in this norm, we will gain that result. It will be helpful for our further estimations, and also matrices should be uniformly elliptic. What about history of this question? What about history of the parametrics? We use the parametrics method, which has been introduced by McKean and Singer, and after that developed by Professor Kinakov and Professor Mamin in 2000. This version differs from the parametrics introduced by Levy, and during our research we dealt with also the article published by Lin, Kalashnikov and Oleinik. But authors freeze the initial space and time points, and we freeze the terminal point. And we freeze only a space point. We do not need to freeze a time point. It's an advantage. Also, we need only a continuity in time variable and hold a condition in space variable. What has done before us, actually before Professor Kinakov, if we know that if we have bounded continuous derivatives, which are under Hölder condition, so the transition density exists and satisfy Kolmogorov backward equation. And so we could consider the parametrics expansion like this. But now, if you remember, I've have not done any assumption about the smoothness of the coefficients. But it could be proved that it doesn't matter in our case. So I don't want to go deeper into the details how to prove the opportunity to expand into parametric series in the case without smoothness assumptions. But in general, we should try this precisely representation as if we know that it could be done. And after that, prove that it's the density of the process. Maybe I will pay a little attention later on its question. And yes, we've written the parametric representation like if we are under the standard assumptions. What does it mean, P tilde and H? P tilde is the transition densities of the so-called frozen processes. That means that in the basic process we freeze point T and Y, so we will gain a process with a Gaussian transition density. So it's a nice property. And what should be mentioned that this is just the function that depends on the coefficients of the starting processes and nothing more. What about H? H is the so-called kernel function. Could be written like here, like if we have two operators and apply it to our density. Also, it's a function which depends only on the coefficients of the starting processes. We could show that parametric series for the first process and for the second processes converge. What about the opportunity to expand into parametric series if we don't have these smoothness conditions? So Professor Kinakov have shown that it could be proved that under our assumptions, this nice function, written just like the sum, is a continuous one with its derivatives also satisfy Kolmogorov-backward equation and could be shown the unicity of constructive fundamental solution and its positivity. So it's precisely our density what we want to have. After that, in the same way as in the article published in 2000, we could show that our frozen densities are less than such some Gaussian density. First derivative less than this guy, and second derivative less than this guy. And please pay attention for that if in the 6 we have integrable times singularity, then in 7 we have non-integrable times singularity. And it will be a problem, but it could be solved. Let us denote the convolution time binary operation just to make our representation shorter. And after that, we could write, also as in the article published in 2000, these estimations. Also, it could be mentioned that our convoluted operator has a nice smoothness property. Yeah? And yes, from these estimations follows that the parametric series converge absolutely uniformly. What about our main question? Yeah? How close the processes are if their coefficients are close enough? We should write difference between our transition densities and rewrite it in the form of parametric expansion. So after that, we should expand the difference between so-called main parts, and after that, the difference between series. And after all, to sum up, we will have the theorem that in our condition, difference between transition densities are less than this guy, where delta n is the difference between our coefficient, and goes to the 0 as n goes to the infinity, and where Pc is Gaussian density. What about difference between main parts? We use just the classical result for estimating the remainder term in this representation, and it could be shown that according to the properties of the Gaussian functions and also according to this estimation for our case, and also with respect to this nice property of the exponent function, it also could be shown that this difference between main parts is less then this guy, then constant, delta n squared, and Gaussian density. So that is what we want to have actually. So that's good enough for a difference between main parts, and we will go to the difference between series parts. Yeah. Yes, squared. In this part squared, I could show you. For main parts, it's squared, and for difference between series, it's just the first power. So in the end, we will have just the first power. Yes. After that, we will go to the difference between series, and we will use lemma. I don't want to go deeper into the details of the proof of this lemma because it's just the technical stuff. Yeah, but the main idea is that we could estimate the difference between R plus 1 convoluted guys with the difference between R times convoluted and something in addition. So to estimate difference between yes, that's like an idea of the inductive step. Yes, inductive method. So for a basic step, we have to estimate difference between these guys. And just to write it using the telescopic sums, we will have this inequality, and we know the estimation for these parts. We know the estimation for the kernel function, and also we know the estimation for the transition density. What we want to have the estimation for the difference between kernel function. So let us denote just for shorter writing first derivative and second derivative is alpha e and beta ij. So difference between kernel function could be rewritten just by definition, like this sum. Pay attention that we know the difference between coefficients according to our assumptions. We know the estimation. We also know this difference according to the Holder properties. And we know estimation for the first derivative. And also we know the difference between coefficient of the main process and of the approximating process. So actually what we want to estimate just difference between first derivative and difference between second derivatives. It can be proved that difference between first derivatives, it's just the technical part also, is less than this fraction. Also it could be mentioned that this is integrable time singularity, and difference between second derivatives are less than that guy, and this is non-integrable time singularity. But as we let me return to that slide. As we know that these coefficients are under Holder condition, and according to the nice property of the exponents, in the end we will gain this estimation, where gamma is the Holder parameter. So this is an integrable time singularity. After that, let us skip to the induction part. Yeah, let us denote as eta r this difference between r times convoluted parts, and then what we know the estimation for the eta 0 and for the eta 1. After that, we will do the inductive hypothesis that eta r is less than this guy. It could be rewritten in more simplest way, just to prove it's easier to write it like this. For basic step, we know that it's true. And we could consider the inductive step. It could be done according to the lemma, which has been mentioned before. That eta r plus 1 could be estimated as eta r convoluted this function. Yeah, actually it's an estimation for the h function, kernel function, plus that guy. Actually it can be computed this less than this guy, and actually this is the proof of the inductive step. We used the properties of beta function and gamma function. And in the end, as the conclusion of the proof, let us return to our basic problem. We want to estimate the difference between transition densities of the process. It's less than difference between main parts plus difference between series. Actually, we've proved that it is less than sums of eta r from 0 to infinity. But we know the estimation for eta r, so it's less than this guy. Unfortunately, according to the mentioned properties of gamma function, the last sums converge. So in the end, we will have the result, which has been mentioned in the statement of the theorem, the difference between transition densities of two eta diffusion processes, which coefficients are close, is less than constant delta n and gamma Gaussian density. I'm sorry. Actually, that's all. What about literature? I've mentioned maybe everything except the last one, but the last one is unfortunately printed only in Russian. And thank you for your attention.
Okay, we have a lot of time. We are well ahead of the schedule, so questions.
I could also think of make an extension and it would be not just also interesting if you look for numerical schemes, then if you have for the numerical schemes you have to choose also some diffusion constant and things like that. It would also be able to find what is the best scheme for the best conversion. Do you see how many different processes and also an extension?
It would be a nice question, but I don't know what would be as a result of this. So I think it's an interesting.
In the term of order delta n and maybe in term of order delta square.
I can't say you precisely at that moment what will be the end, but it's interesting questions. Okay. And actually, we will be very thankful if somebody knows some similar results or maybe some results on this topic. So we are open for your asking.
And I think that if we continue this daily extension, then we can get extension. But example, I can mention some example where such perturbated diffusion occurs. For example, in a recurrent estimation problem like Lorenz monoropoulos and so on. Then we have some perturbated diffusions with perturbated coefficients. Or if you make some smoothness of coefficients with some delta function type function. Another diffusion, then it's the question, natural question is how close are the transition densities. But I think that for the main terms also we should have why delta square? Because only the difference of means and but it's maybe we can discuss it.
Yes.
Any more questions?
So you compare to density, I guess, in the
It's uniform norm for all bits y and
so I mean you can also look at something. Actually, this should be the same correctly. The marginal densities should they took out distributions here, or so what is?
it's a transition density of the interdiffusion. We've started. It's not Gaussian in the general case.
No, but what I mean, I saw similar studies, but they compared the density not in the supernorm, but something like a total variation. If you compare to total variations, measure of different sets, then it can be expressed via supercollateral divergence of measures. Somehow it gives another answer, something like difference between two measures in the mean.
In what the article you mentioned?
No, it's if I can. It was a talk. I'm not sure that there is a paper published. Connection to one-to-one Monte Carlo.
Okay. Could you please show the metrics, yes, I mean gamma plus gamma over 2. I didn't get the idea where you get this type of, on the lower line here. Ah, okay, this is for x and this is for t.
Yes. That's the difference between x and t. That's just the definition of the parabolic graph.
It's enough to consider T1 equals T2 in this paper because and it's enough to consider simply Hilbert space without time and just say that constant is uniformly in T. Hilbert space is some uniform constant. It's a little bit bigger because it's also possible to impose such assumption.
No questions?
But I don't understand why there is gamma and gamma over 2. Is it some
Because gamma over 2 it's about with respect to time. Gamma
Yes.
with
Where
respect to
they,
space
where
period.
they are different.
Because it's so-called parabolic distance.
Ah.
And you consider x1 minus x2 absolute value plus t1 minus t2 absolute value 1/2 to the power.
It looks like diffusion, maybe somehow. Okay, thanks.
Okay, let's spend on again.